All right, so I wanted to make a screencast of object thrown up, okay, thrown upwards. So I'll just write object thrown upwards, object thrown up, moves up, and now it's on its way down. And I really just want to kind of show you that in all cases your displacement is going to be 1/2 AT squared plus V naught T. But these are actually vectors. This is actually a beautiful vector relationship. You've probably been thinking about it as an equation, but it's not. It's not really just an equation. It shows you how these vectors are really related, how they add together to make your displacement. Anyway, so hopefully this kind of illustrates that. I'm going to define down as positive direction, okay? And I'm going to say an object is launched. There's my beginning velocity. There's my velocity at later time, later time, later time. And then eventually my velocity is like really small. Maybe it's 0 at that moment. And then on the way down, the velocities are the same exact length. So I'm going to try to do those arrows the same length so they correspond. Now this one, I'm not going to draw another arrow. I'll just stop there because it's on its way down. Hopefully, though, you see that your acceleration never changed. So I'm going to draw my acceleration arrows kind of in the same spot, starting at the same location. And I'm just trying to show here that my accelerations didn't change. My velocities are what changed. All right, and we can justify this several different ways. Now, in terms of the graphs, I'm just going to focus on my velocity and acceleration graph because that's where a lot of richness is at this point. You should know that your net force graph will look exactly like your acceleration graph, and you should also be able to draw a position time graph. But for now, let's just make this our focus, please. All right. And I'm going to start with the easier one. Since I made down positive, my acceleration is positive. And this area is going to be a times t, which is my change in velocity, which is a t. Okay? And this is a vector relationship. Change in velocity is a vector because velocity is a vector. Final velocity minus beginning velocity gives me my change. And final velocity, therefore, is a vector that's equal in length to my acceleration time vector plus my initial velocity vector. Okay? And I can illustrate this pretty simply. I can say, all right, my change in velocity vector, if it looks like this, then that is identical to my acceleration time vector, right? These vectors have the same magnitude, this vector and this vector. And even more cool, I can take v final and subtract from it my initial velocity. My initial velocity is up, so now my initial velocity would be down. Now that's a pretty long vector. So there's my initial velocity, but now it's reversed in direction. So my initial velocity vector reversed in direction. So now it's negative. Initial velocity vector plus my final velocity vector, which, as you can see, my final velocity is much smaller. And these vectors add to give me my AT vector, or they add to give me my change in velocity vector. Now, a really cool part is if we look at our velocity graphs area, okay? So let me do that. I'll try to draw it reasonably here. Something like this, right? It started in the negative direction because it was moving up in the negative direction as I've defined it. I defined down to be positive. Now, if you notice, I can make a symmetry argument. Now, I wanted to sort of convince you that like in all cases, this vector relationship gives you your displacement. And this is actually a pretty hard example. It took me a while to figure out a way to show you. I'm going to give you a geometric argument. These two areas are the same, right? And one area is a positive value, the other is a negative value, so those add to 0. So really, it's the area of this shape, this trapezoid, that I want, okay? So I just want to point that out. That area, the area of that trapezoid as I've drawn it, is our displacement, right? That's what I have here. Okay. Now, if I take, let's see. Now this relationship only holds true if we actually add the vectors as vectors. So drawing out this vector relationship, if I'm on the way down, my displacement is still up because I've not yet reached the location where I was launched from. If I'm a projectile thrown up and I moved up and now I'm on my way down, my displacement is up, right? Well, the only way that's going to happen is when, let's see here, your initial velocity vector is so large. In fact, your v naught t vector has to be larger. This vector has to be larger than my 1/2 at squared vector. So that would be worth thinking about for a while. That's pretty difficult. So take that in for a minute. Again, I'm going to argue that since my displacement is up, my initial velocity times time vector has to be a greater length than my 1/2 at squared vector. Okay? Now, to prove that to you, oh gosh, okay. So why don't I look at this rectangle? This is my initial velocity. This is my final velocity, right? So this triangle right here, yeah, this is a t. So let me get rid of that t1. This is a t, the height of that triangle, right? The area of that triangle is going to be 1/2 at squared, right? If I take v naught t, okay, v naught times t, so let's shade these in. I'll put dots here to show this triangle, okay? Now, that's going to be 1/2 at squared. So that triangle is that. Now, this part, this v naught t, is actually this rectangle, right? So if you think about it, then the magnitude of your v naught t, so whatever number you get when you multiply v naught times t, that magnitude, because v naught t is larger, looking at my vector diagram, my v naught t's area, that's this area here, minus my 1/2 at squared area, which is this triangle here, right? Well, what does that have to be? Well, this cancels out with this, so that leaves that trapezoid, which is my displacement. It's sort of beautiful, dude. Anyhow, hope you enjoyed that. That's pretty much, that's the punchline right there. Whenever you have a constant acceleration, this is a true vector relationship that holds. And what you're going to find is this doesn't just work with one-dimensional motion. Things can get quite interesting for us, and it can all make sense if you see how the vectors are related to one another. Anyhow, I hope you enjoyed it. Hope it helps, and have a good day.